I'm Julianne DeSalerans, and I'm going to be going through a PowerPoint presentation today on our circular dichroism spectrophotometers. Thank you for joining me. My first order of business is to share screen. So I will do that now and begin from the beginning with this presentation. It's about a 35 page slideshow that ends in a tabular comparison of us versus them. So we got into circular dichroism in the 1990s, about 20 years after our company was founded. I just make the point here that we're very fond of our product names. We kind of choose them once and rarely change them, if ever. But our product evolution and improvements are continuous. The model DSM 20, 1000, and 17 will be the models that we focus on in this presentation. A comment that we make around here all the time, a reminder, is that in circular dichroism, everything conspires against you. You're making a measurement in the deep ultraviolet region where there's very little light. You're looking to see sub-milli-absorbance signals. This, of course, is a differential measurement. Your light-absorbing solvents, water, as an example, like to eat up all of your available light, and you're typically dealing with very short path length cuvettes. And yet all non-OLIS CDs use only 50% of the available light, which seems a very strange oddity given that this is a absorbance measurement where it's all about light. Only the ordinary beam is used, the extraordinary beam is not. Compare this with what we realized we could do, which was take advantage of both the ordinary beam and the extraordinary beam, giving us therefore twice as much light to work with. The old style way of doing CD, which tragically is still being done by all of our competitors, involves not only utilization of only 50% of the light, but complex electronics to find, isolate, and amplify the CD signal from the single beam of light. And this is done using a lock-in amplifier. Our method, on the other hand, exploits extremely powerful software for finding the left and right information in the raw signal. The correct answer is the only answer possible. So in an OLIS DSM CD, digital subtractive method circular dichroism, a beam splitting polarizer, like everyone uses, produces two spatially separated beams. These two beams pass through, in our case, one sample diverging at 3 degrees from each other until they reach 2 detectors. 2 scans are collected and averaged de facto. And what's returned is a single scan with a square root of 2 better signal to noise than one gets from a single beam system. These two beams of light, these two scans, are therefore identical to each other, except they're 180 degrees out of phase. Each contains 500,000 points each per second. Every datum along the photoelastic modulator's sinusoidal transition curve is tagged as contributing to left or right. Very sophisticated math follows, and the exact circular dichroism is calculated from the raw signals, not those already processed through a lock-in amplifier. No calibration constant K and no lock-in amplifier are used. Here you see that what we're doing is we're literally, as anyone, the machines do, pass left, right, left, right, left, right through. But we wound up developing the math thinking about using both beams. We ultimately realized that the two beams were sufficient unto themselves. So we also have a single beam instrument that still exploits the freedom from the lock-in amplifier and the direct acquisition of absorbance left minus absorbance right. Here is an actual CD chamber showing the photoelastic modulator, the cuvette position, the 2 beams of light traveling to the 2 awaiting photomultiplier tubes. And optionally here, we can put 2 cuvettes for independent collection of 2 samples, or in this port, we can put a right angle detector for fluorescence detection. Here we have one of our instruments, the DSM 17 CD, with this dual beam sample compartment on it. Here's our 2 photomultiplier tubes. There's our photoelastic modulator. Here's our water lines coming in and out for temperature control. There's the port for the fluorescence detection. And in this model, the 17, we're utilizing the extraordinarily good prism grading monochromator originally manufactured by Carey. We choose these for their near infrared capability. As I mentioned, after several years of doing this strictly dual beam, we were like, we can use just one of these beams. So we developed a sample compartment for single beam detection, still exploiting all of the technology that we had pioneered around the math and whatnot, and came up with something that we call the Polarization Toolbox. This is a single beam sample compartment with accessible polarizer and photoelastic modulator, allowing you, the investigator, the experimentalist, to position your hardware, your polarizer, out of plane, in plane, before the sample, after the sample, and likewise to move the photoelastic modulator. In this particular picture, we have a 4-position turret in place so that you can set up very long experiments without any user intervention. And of course, what really drove us towards the development of this was circularly polarized luminescence. However, MCD is another application where we were doing single beam CD. In this picture, we show our 1.4 Tesla magnet in place. There's the photoelastic modulator. In this picture, we show that Polarization Toolbox sample compartment sitting on the carry instead of the dual beam detection system that we saw earlier. This particular one has a very long railing because it's going to be used with a cryogenic magnet. Here we have the same carry instrument now also with the toolbox, but with the addition of an emission channel. This is where we're able to now do circularly polarized luminescence. So the OLIS DSM 172 is one of the only instruments in the world capable of doing CD and CPL. We happen to also make the other one, the OLIS 245, which I won't be talking about in this presentation, but I'd be happy to some other time. This is again one of our dual beam systems. There's again the 2 photomultiplier tubes, but this one is set up for a very long cuvette holder that has actually 6 cuvette positions. Real world situation, here's the tiny little OLIS DSM 20 CD, the same dual beam CD chamber that we've been talking about, but instead of the large carry monochromator being over here, it's our small hummingbird monochromator, so named because it's very small and fast and precise. These are then your water lines coming out for use with a water jacketed cuvette holder. Peltiers don't require that extensive cooling. So the OLIS DSM 20, just while we're on it, uses that small subtractive double grading monochromator that we named the Hummingbird. As you see asterisk down here, one of the interesting attributes of a subtractive double grading monochromator is that it outputs a homogeneous beam independent of the path length. So it doesn't matter if you're working with 1 nanometer or 10 nanometer light, it's fully blended, it's homogeneous, and that's what the sample sees. So there's no concern about one part of your sample seeing one wavelength and another part of your sample seeing a different wavelength. It's a beautiful, perfect, homogeneous blend. It happens to be the smallest CD made. That was one of our intentions when we designed the Hummingbird, and it has brilliant light throughput, 170 to 700 nanometers, making it ideal for effectively all circular dichroism applications. The OLIS DSM 1000 is based on our patented rapid scanning monochromator system. Again, the dual beam CD chamber here. Here we happen to have the nitrogen flow valve sitting out front. The control box, all of our electronics are external, and these are miscellaneous power supplies for the lamp, and a closed cycle cooling water system for our lamp. And we'll discuss that later too. The 1000, again, uses our patented, also subtractive double grading monochromator, but this one with a moving intermediate slit, which extraordinarily allows you to do up to 1000 scans per second, not in CD, mind you, but in absorbance and fluorescence. This one is slightly higher light throughput in the UV. It has a shorter wavelength range, but it can be extended easily. I say here 700, it can go beyond that. With a different pair of gratings, which are very, very easy to exchange. These are just some of the accessories that you're going to see. This is our titrator, a stop flow, a variable angle thin film holder. This is the magnet, a Peltier cell holder, a cryogenic flask, some of the accessories that you might choose to use with any of the OLIS instruments. DSM, again, digital subtractive method supports linearity over 4 orders of magnitude. It probably goes considerably beyond that, but we didn't bother to measure it. It's still an extraordinary breadth. And this graph very nicely shows that you've got very useful light even below 170 nanometers. Here we're only at 500 out of a maximum of 1100 on the models 20 and 1000. The 17 and 172, because they are working with the carry spectrophotometer, have a physical limit of 185, but they go into the near infrared as far as 1700 nanometers. Temperature dependent work is something that many people do in circular dichroism. We give you the ability to, of course, collect and view your spectra in a 3-dimensional format. This is a thermal profile that we extracted from a single wavelength. In this case, it looks like it was 220 out of the full record that was 250, 190. And then we provide inside the OLIS software the mathematics for doing very sophisticated and correct and easy and instantaneously fast analyses of these data so that you wind up with the answer that you did the experiment for. What is my species that I was starting with? Typically my native protein. What is the unfolded protein? What is their transition temperature? And what is their enthalpy? And here you have their enthalpy returned and the transition temperature. This is all done even more quickly than I've taken us through the slides. This just happens to be a very interesting publication that came out back in 2002 that was published in Biochemistry. Without integrating spheres, moving sample stages, or other complication, the dual beam OLIS DSM CD acquires credible spectra from particulate sample preparations. Again, one wants to have your sample as clear as possible with CD, but knowing that ours is a little bit better with samples that aren't perfectly clear is comforting. Here is an example of the near infrared performance that would be possible from the 17 or the 172. And in this case, we show spectra to about 1300. The in-gas detectors that we have available can take us to around 1700 nanometers with obviously beautiful fidelity. Those are lovely spectra. So DSM collects CD by definition. We are directly acquiring absorbance left and absorbance right. The answer can only be correct. There's no requirement, therefore, by you, the user, to know anything about the appropriate amplitude, sensitivity, or time constant settings that the lock-in amplifier requires. When you're using our dual beam configuration, you're using 100% of the light. It's linear over many orders of magnitude, has 0 drift, allowing you to do exceedingly long experiments without concern about drift. No factory, no post-factory calibration, because there is no calibration. There's no calibration constant. It's done through the software. The answer can only be correct. So now we get into the numbers that a lot of people like. I've put some text over here to the far right, expanding on some of the points. I won't go through too much of this. You're obviously free to look at it at your leisure. But indeed, wavelength accuracy, reproducibility, resolution, all these wavelength range, etc. They're all going to be extremely similar, one instrument to the other. Scanning speeds, you're never going to scan rapidly in CD. I mean, unless you have a very large signal and you've got just a very sweet opportunity, but most of the time you're scanning rather slowly. LD, that's a measurement that has been around for decades. Some laboratories do it very successfully. You can use ours for that, but we don't make a big point of using it. Again, the lock-in amplifier, let me get this out of your way here, is not used in the OLIS instrument. And so you are doing, again, CD by definition, no lock-in amplifier. All of our modern electronics and software allow you to deal with that. Some people have talked about doing capillary sampling with a CD. Seems a little iffy to us, but if you want to try it, we're not going to stop you, of course, but we haven't tried it ourselves. Birefringence of non-flat surfaces, it's a concern. What else? Yeah, integrating sphere, it's not CD. Diffuse reflectance CD is a misnomer. It's a reflectance measurement, whereas circular dichroism is an absorbance measurement. So it's giving you what we refer to as an artificial approximation of CD. If you want to work with really turbid samples, we suggest that you look at our clarity line of UV-Vis instruments addressed elsewhere. Circularly polarized luminescence. This, of course, is something that many people interested in CD should also be interested in. If you're working with samples which are emissive, you should have CPL. And as we've shown, the 172 is one of our 2 models that supports both CD and CPL. We also have a freestanding, much lower priced instrument for just circularly polarized luminescence, which we call the Solo. So ask me about that. And then, of course, our software. None of what we've done would be possible without extraordinary software. And, this company was founded in the 1970s by my dad, Dr. Richard Tassah, who was computerizing his own instruments at Cornell back in the 1960s. When he took faculty position at Georgia in the 70s, he was consistently publishing about this work, and people started coming to him saying, I'd like to have the same. So OLIS spectrophotometers from the beginning put the emphasis on the software, which allows us to eliminate a lot of complicated electronics and old-fashioned ways of doing things. So brilliant breakthroughs happen. Ours can lead to yours. UV-Vis and near-infrared spectrophotometry systems for best results. We're always going for the right answer. We're always going for the best results possible and least waste. The least time, the least consumables, the least experiments. It's all for the good. Don't aspire to less. Circular dichroism is hard enough without unprofitable effort and squandered resources. So I'd love to talk with you in more detail about which of the models would be best for you. And I'm going to now stop sharing and say thank you very, very much for your time. And our number is 1-800-852-3504. Internationally, that's 1-706-353-6547. And you can reach me at Julie, Julie, at olisweb.com. Looking forward to hearing back from you. Thanks.